we're going to look at a couple of examples of integration by partial fractions. Now, partial fractions is useful when we have a rational function whose numerator has a degree that's less than the degree of the denominator. If the degree of the numerator is greater than or equal to the degree of the denominator, you would use long division as an introductory step. But these are basic examples, and we won't be doing that. Now, I might be tempted to use ordinary substitution in order to evaluate this integral. If I take the derivative of the denominator, I would get 2x minus 4. However, the numerator is not a constant multiple of that, and so substitution fails. What we need to do in order to do this is take the denominator and factor it. What's nice about this is then that the entire fraction can be written as simpler fractions, a sum of two simpler fractions where we have a constant over x minus 3 plus some other constant over x minus 1. These two integrals are easy to evaluate. What we do now is multiply both sides by the denominator. What will happen is here the x minus 3 will cancel with this x minus 3 for the first term, leaving the factor of x minus 1. And when I multiply x minus 3 times x minus 1 by the second fraction, the x minus 1's will cancel, leaving an x minus 3 multiplied by the b here. There are lots of ways to do this. I think the simplest way is to choose particular values of x that will eliminate one of the constants. Okay, this is supposed to be an identity, which means it should be true for all values of x. Now we're going to take a little bit of leeway because over here I really couldn't substitute all values of x, but I will here and we'll get the constants we need. If I let x be equal to 1, then I'll get a times 1 minus 1, which will be a times 0. Over here I'll get b times some non-zero quantity, and that will allow us to solve for the value of b. So we let x be 1, we're going to get 3 times 1 plus 1, a times 0 essentially, plus b times negative 2. So we end up with 4 is equal to negative 2b, and b is negative 2. So now we know that this b is negative 2. Just a little recap, this is what we were looking at. Here's the equation that we were playing with before. When I chose x equal to 1, it got rid of that term. Now if I choose x equal to 3, it will get rid of this term, and I'll be able to figure out what a is. When x is 3, we get 3 times 3 plus 1, so that's going to be 10. A times 2, and then b times 0. So b will go away. We'll have the equation 10 equals 2a, which means that a is equal to 5. And now it's a pretty straightforward integral. So our integral becomes this new integral, right? We had a over x minus 3 plus b over x minus 1. Just substitute the values of a and b that we found. There's a, that's what goes there. And now these are nice integrals to evaluate. What function's derivative is 5 over x minus 3? Well, the natural log of x minus 3, the absolute value of that, times 5. Minus 2 times the natural log of the absolute value of x minus 1. Our second example is a little bit more complicated because we'll do the same sort of thing. Notice the numerator has a degree less than the degree of the denominator. We follow our previous instructions and factor the denominator, which in this case becomes 2x minus 1 squared. When we have squares, it's a slightly different method. What's going to end up happening is our original fraction is going to be some constant over my linear term to the first power here, plus some other constant over the entire fraction. Okay, again, substitution does not work here. The derivative of 4x squared minus 4x is 8x minus 4. This is not a constant multiple of that. So what we'll do this time, again, we'll multiply both sides by that denominator, clear things out. That leaves us with one factor of 2x minus 1 multiplied by a because only one factor will reduce. I can choose a particular value of x that will eliminate this. If x is 1/2, 2x minus 1 becomes 0. So we choose x to be 1/2. 3 times x, 3 times 1/2 plus 1. is equal to 0 plus b. Well, if I work things out, that's 3 halves plus 1 is 5 halves. That's 0, so b is equal to 5 halves. Now, in order to figure out what a is, I can't pick another value of x that will eliminate b because b is not even multiplied by anything. So what I'll do is I'll take my equation and substitute b in. So just, again, a refresher as to where we were. That's what's in the little orangish area. So b was 5 halves. And now we can choose any x value we want. The easiest x value, I think, to choose is 0. You can't always do that, but in this case we can. If x is equal to 0, we get 3 times 0 plus 1 is going to be a times 2 times 0 minus 1, so that's going to be negative 1. That's equal to 5 halves, or plus 5 halves. So 1 is equal to the opposite of a plus 5 halves. If you subtract 5 halves from both sides, we get negative 3 halves on the left side, and multiply through by a negative 1 to make it positive a, we get a equals 3 halves. We're going to put these values in. I don't actually put them in the numerator, I just put them out in front, 3 halves and 5 halves. And now we use other integration techniques. You could use substitution. I like to kind of use backwards thinking instead for these things where we have linear pieces like the 2x minus 1. For instance, I know that in order to get this into the denominator, we'd have to take the natural, or have a natural log of something. But if I take the derivative of the natural log of 2x minus 1, I would pop out an extra factor of 2, and in order to compensate for that, I have to divide by an extra factor of 2. So I went from 3 halves to 3/4. That 4 in the denominator will compensate for the 2 that pops out with the chain rule. Similarly, over here, this is 2x minus 1 to the negative 2 power. We raise the power to negative 1, divide by negative 1, that's where this negative came from. But in order to compensate for this 2, we take the 5 halves and divide by 2, giving us 5/4.